All right, welcome. Today we're diving into Python modules, and honestly, once this clicks, it changes how you write code forever. We're talking about modular programming, breaking your code into clean, reusable chunks instead of dumping everything into one giant file. By the end of this, you'll be writing smarter, more scalable Python. Let's get into it. So, what even is a module? Simply put, it's just a .py file. That's it. You write some functions, maybe some classes or constants, save it as a .py file, and boom! You've got a module you can import anywhere in your project. Think of it like Lego bricks. Each brick does its own thing, and you snap them together to build something bigger. The big wins here are organization, keeping related logic in one place, reusability, write it once, import it everywhere, and namespace isolation, which basically means your variable names won't step on each other's toes across different files. Super important once your code base starts growing. Okay, let's actually build one. Create a file called greetings.py. Inside, write a hello function and a goodbye function. Nothing fancy, just return an f-string with the name. That's your module. Now, in a separate file, main.py, you just do import greetings and then call greetings.hello with a name. Run it, and you'll see hello Alice printed out. That's the whole loop. One pro tip here. Keep your modules focused on one responsibility. Don't make a module that does math and file handling and sends emails. Single responsibility makes testing way easier down the line. Now here's something that trips up a lot of devs early on, the module search path. When you write import something, Python doesn't just magically find it. It searches through a list of directories in a specific order, and that list lives in sys.path. First, it checks the current directory, wherever your script is running from. Then it looks at Python path, which is an environment variable where you can add your own custom paths. And finally, it checks the standard library and site packages. That's where everything you install with pip lives. So if Python says it can't find your module, 9 times out of 10, it's a path issue. Check sys.path in the REPL and you'll figure it out fast. Let's talk import syntax, because there's more than one way to do this. The most basic is just import math. Then you access everything with dot notation, like math.py, clean and explicit. Then you've got from math import sqrt. This pulls just sqrt directly into your local namespace, so you can call it without the prefix. Super handy. Then there's aliasing. Import numpy as np. This is basically a community convention at this point. Everyone does it. And finally, wildcard imports. From math import star, just don't. It dumps everything into your namespace and you lose track of where things came from. One more thing. Watch out for circular imports. If module A imports module B and module B imports module A at the top level, Python's gonna have a bad time. Refactor shared logic into a third module to break the cycle. Alright, let's talk stlib, the standard library. Python ships with a massive collection of built-in modules and you don't need to pip install any of them. 4 that you'll reach for constantly. Math, for anything beyond basic arithmetic. Square roots, logarithms, pi, factorials. S, for interacting with the file system. Joining paths, listing directories, reading environment variables. Datetime, for working with dates, times, and durations. Trust me, you'll need this more than you think. And sys, for low-level runtime stuff, reading command line arguments with sys.argv, or exiting a script cleanly with sys.exit. These 4 alone will cover a huge chunk of your day-to-day Python work. Here's a quick cheat sheet to keep handy. Math gives you floor, ceil, factorial, sqrt, log, and the constant p. OS covers path.join, listdir, getcwd, environ, and makeDirs. Datetime has datetime.now, starftime for formatting, time delta for durations, and UTC-now. And sys gives you argv for command line args, exit, path, version, and platform. Again, none of these need a pip install. They're all baked right into Python. Just import and go. Once your project grows beyond a handful of files, you'll want packages. A package is just a directory with an dunder_init.py file inside it. That's _init_, by the way. That file is what tells Python, hey, Treat this folder as a package. Inside, you put your modules. So you might have mypackage/module1.py and module2.py. To use them, you do from mypackage import module1, or go deeper with from mypackage.module2 import helper. Packages are how you keep large codebases navigable. Without them, you just have a flat pile of files and no one wants that. Now let's go one level deeper. Subpackages and relative imports. You can nest packages inside packages. So imagine my project has a core subpackage and a utils subpackage, each with their own dunder init.py. Inside core/engine.py, you can use relative imports. A single dot means current package, double dot means go up one level. So from .utils, import helpers goes up to my project and then into utils. That said, best practice is to prefer absolute imports. They're clearer, easier to read, and less likely to break when you move files around. Use relative imports only when modules are tightly coupled and you know they'll always live together. This is a pattern every Python dev needs to know. Every module has a dunder name variable. That's $name. When you run a file directly with python calculator.py, dunder name equals the string dunder main. But when you import that same file from somewhere else, dunder name equals the module's actual name, like calculator. So the pattern is, wrap your runnable code in if dunder name equals dunder main. That way, your functions are always importable, but the demo or test code at the bottom only fires when you run the file directly. It's a small thing, but it's one of those Pythonic habits that separates clean code from messy code. Alright, that's a wrap on Python modules. Go build something modular. Alright, so here's something that trips up a lot of devs when they're working in the REPL or an interactive notebook. You import a module, you tweak the source file, you call import again, and nothing changes. Why? Because Python caches every module in sys.modules the moment you first import it. So that second import call, it just grabs the cached version and moves on. To actually pick up your changes without killing the interpreter, you use importlib.reload and pass in the module object. Now, and this is the gotcha, any instances you already created from that module, they're still pointing at the old code. The reload only affects new references going forward. And if you used from my module import my function syntax, reloading the module won't update that name in your current namespace. You'd have to manually re-import the specific function. So just keep that in mind. Stale code can sneak in silently if you're not careful. Okay, so let's talk about what actually makes a module good, because slapping some functions in a .py file isn't enough. The big two are comments and docstrings. And yes, they're different things. Comments with the hash symbol are for the developer reading the internals. They explain how the logic works, the why behind a tricky bit of code. Docstrings, on the other hand, are for the user of your module. They explain what a function does, what it expects as inputs, and what it returns. And docstrings aren't just nice-to-haves. They power the built-in help function. They're what your IDE uses for IntelliSense autocomplete, and they're what tools like Sphinx use to auto-generate documentation. The real pro move is combining docstrings with type hints. When you do that, your API basically documents itself, and future you will be very grateful. So once your project grows beyond a single file, you're going to want a package. A package is just a folder with a dunder init.py file inside it. That's $init by the way. That init file is your package's public API. Whatever you import inside it is what consumers of your package can access directly from the package name. So in this example, we've got an analytics package with 3 internal modules: loader, processor, and reporter. In the dunder init, we re-export the key functions from each. Now in main.py, the caller just does from analytics import load CSV, clean data, generate report. Clean and simple. They don't need to know or care about the internal file structure. That's the whole point. You hide the implementation details and expose a stable, clean interface. Let's make this concrete with a classic example, a modular calculator. The idea is simple. Pull all the math logic out into its own module called operations.py. You've got add, subtract, multiply, and divide. And divide has a guard clause that raises a value error if someone tries to divide by 0. Then, in main.py, you just import the functions you need and call them. That's it. Now here's why this matters. If you ever need to swap out the math logic, add new operations, or write unit tests, you do it entirely in operations.py. You never touch main.py. That separation of concerns is what makes code maintainable at scale. All right, 3 best practices you should burn into your workflow. First, naming. Always use lowercase with underscores for your module file names. Something like data_utils.py. Avoid camel case, avoid generic names like module1.py. Those are red flags that the code wasn't designed to be reused. Second, documentation. Every public function and class needs a doc string, no exceptions. Pair those with type hints, and you've got a self-documenting API that any dev can pick up without reading the source. Third, testing. Get in the habit of writing unit tests alongside your modules. The example here uses Python's built-in unit test module. It's stdlib, no extra installs needed. If your module is well designed, it should be trivially easy to test in isolation. If it's hard to test, that's usually a sign the design needs work. So where does all this actually show up in the real world? Everywhere, honestly. When you're building a web API, say with FastAPI or Flask, you split routes, models, schemas, and services into separate modules. A new dev joining the team can find the user routes in routes/users.py without wading through thousands of lines of spaghetti code. In data engineering, you chain loader, transformer, and reporter modules together to build ETL pipelines. That's extract, transform, load, where each stage has clear ownership and can be swapped independently. And for automation scripts, you package your file handlers, schedulers, and notifiers separately so you can update one piece without breaking the whole system. Bottom line, modular design isn't just good practice. It's the foundation of every Python project that actually survives contact with production.